We're going to give you a solving strategy for problems concerning Newton's laws. First of all, you have to specify all the forces acting on each body and draw the body or the bodies that exist in the problem. Now draw a free body diagram for each body in the problem, and the free body diagram represents all the forces in the coordinate system you choose to solve the problem in, where the body does not exist in this diagram. That's why it's called free body diagram. After representing the forces as vectors in this diagram, you have to break up these vectors into their components if it is needed. Then you need to find the net force out of these vectors by adding the components along each axis. Well, by considering the signs, of course, where the sign to the positive is the sign of the components along the positive x-axis are positive, and those along the negative x-axis are negative, and likewise for the y-axis, the components along the positive y-axis are going to be positive, and those along the negative y-axis will have a minus sign or negative sign. Then afterwards you should write the Newton's law for both axes, where the resultant force along the x-axis give us the net of the x component, that is the product of the mass by the acceleration along the x-axis a sub x. And similarly, the sum of the components along the y-axis give us the net force along the y-axis, that is the mass multiplied by acceleration along the y-axis. Now you have to specify your knowns and your unknowns, and then you solve your equations for the unknowns. You should use the proper signs, as I said before, when you are substituting your forces or values in the above equations. And you have to decide in which direction is the resultant along the x-axis or the y-axis. Obviously, the resultant is going to be in the direction of the larger force. About the forces of friction, as you know, we have two types of forces of friction. There is a force of static friction, and there is a force of kinetic friction. This diagram demonstrates the case of static friction. The force of friction, as we said before, it represents the resistance to the motion of a body on a rough surface. This is because of the interaction between the body and the surface. In this diagram, the block of mass m is set in static equilibrium. How can we tell that this mass is in a static equilibrium? If the resultant force along the x-axis equals 0, and the resultant force along the y-axis equals 0, this means that the block is in a static equilibrium. Now, if you can see in the diagram, there is an applied force acting towards the positive x-axis, and there is a force of static friction trying to prohibit the mass from moving and keep it in its position. So the applied force has a positive sign, and the force of friction obviously has a negative sign. That is equal to 0 because it's not moving. And then in this case, the applied force is equal to the static force of friction. However, along the y-axis, also the resultant force is equal to 0, and there are two forces acting on this block along the y-axis, the force of gravity downward and the normal force upward. Then Fn has a positive sign, while mg has a negative sign, and the result is the normal force is equal to the weight of the block.
Did you ever wonder why objects slow down and then stop after they're given a push? This glider stops very quickly after it is sent sliding along the track. But when the glider is floated on a cushion of air, friction is nearly eliminated. Now the moving glider slows down only gradually.
Now, to understand what do we mean with the maximum force of static friction, now we can apply a force along the x-axis, and in a time where we apply this force, the static force of friction prohibit the force from changing the state of motion of the mass. Then we keep changing the applied force, and then we'll find that the static force of friction also prohibits the block to move, because the applied force still is not overcoming the static force of friction. Then we start increasing this applied force until we reach to a stage where the applied force is about to overcome the static friction. And in this case, we're going to say that the mass of the block M is on the verge of slipping. This means that the mass is just about to move. This is the borderline between the block being static and the block being moving. If we reach this stage, this means that this static force of friction is the maximum. And in this case only, we can set the static force equals μs times Fn, where Fn is the normal force and μs is the coefficient of static friction. This is a characteristic of the friction between the two bodies, the blackboard and the object. So again, only the static force of friction, which has this equation as a product of static coefficient of static friction and the normal force. Now again, if you want to check the equilibrium along the y-axis, we're going to find that the resultant force or the net force is equal to 0, because the block is not moving up, neither moving down. And then we'll have then Fn minus mg equals 0, that is Fn equal to mg, and this is the simplest case where the normal force equal to the weight of the object. Along the x-axis, we're going to have applied force minus the static force friction at the maximum equals 0. By substituting the static force friction at the maximum from here, we're going to get μs multiplied by normal force equal to F applied. From here, we can find the coefficient of static friction as the ratio of the applied force divided by the normal force. And as long as the normal force equals to mg from this equation, we put it in here, and we'll get this result where we can evaluate or determine the coefficient of static friction.
Any two objects being rubbed together have frictional forces between them. How do those forces depend on the area of contact between the objects? We'll use this long board and a spring scale to find out. If we pull the board along the table with its widest face down, the amount of force required to overcome static friction is about 12 newtons. If we now tip the board up on its edge so that the surface area in contact with the table is decreased about 4 times, how much force will be needed to move the board? The force remains about the same. To a good approximation, static frictional force does not depend on the area of contact.
This incline has 4 different surface materials: rubber, wood, sandpaper, and Teflon. Identical brass blocks are placed on the 4 surfaces. Now the board will be tilted until each of the blocks starts to slide down. As the board is tilted, the blocks begin to slide in a definite order. We'll repeat this sequence with the angle of tilt displayed next to the board as each block slides. Here are the angles at which each of the blocks started to slide on the various surfaces.
How does the friction between two objects change as the force pushing them together is increased? We'll use this long board, a spring scale, and some weights to find out. If we pull on the board with the spring scale, we will notice that the board always starts to slide at about the same force. This is the maximum value of static friction. If we add enough weight to the board to double the overall weight, how will the required force change? The force needed to move the board approximately doubles. If we now add another weight equal to the weight of the board, tripling the original weight, we see that the force is approximately tripled.
The second type of force of friction is the force of kinetic friction. And here we're going to compare the force of kinetic friction to that of the previous case of the force of static friction. When the block of mass m is moving with a constant speed under the action of an applied force of this one, obviously the object is moving with a constant speed under the effect of two forces, the applied force to the right and the frictional force to the left. When the net force is equal to 0, this means that the acceleration is 0, and then the mass is moving with a constant velocity, because the derivative of the velocity is the acceleration, and if the acceleration is 0, this means that the net force is 0. Again, if the net force is 0, this means that the force applied to the right is equal to the force applied to the left, that is the force of kinetic friction. And the force of kinetic friction is defined at any instant of time while the block is moving, as defined as the coefficient of kinetic friction times the normal force. As we notice here that the two friction bodies has two coefficients for the friction. One for static friction and the other for kinetic friction. And along the y-axis, obviously the resultant force along the y-axis is 0. That is the normal force equal to the weight as we got that before. And then along the x-axis, the net force equals 0, as we said before a while. This case means that the applied force is equal to the force of kinetic friction. And from here also we can get the coefficient of kinetic friction as the ratio of the applied force divided by the weight of the object. If we compare the force of kinetic friction, we can find to that of the static maximum force of static friction, we can find that we have always Fk less than the maximum force of static friction. This indicates that mu k is always less than mu s. That is, the coefficient of kinetic friction is always less than the coefficient of static friction.
Static friction between this wooden block and the table keeps the block from moving until it is pulled by a sufficiently large force. We'll use a spring scale to measure the force required to overcome the force of friction and move the block. In this case, the force is approximately 23 newtons. The force needed to slide the block along the table at a constant speed is less than 23 newtons. The coefficient of kinetic friction is lower than the coefficient of static friction.
If a glider is at rest on a track and the track is shifted from side to side, the glider will move with the track. Air is now forced through holes in the side of the track so that the glider is supported on a cushion of air. What will happen now if we shift the track from side to side with the air turned on? The glider is now motionless. If we give the stationary glider a single push, it moves at a constant speed after the force is gone.
This is a typical example that shows the effect of frictional force on a moving object. In this example, a skater of mass 60 kg has an initial velocity of 12 meters per second as shown. He slides on an icy road where the frictional force is 36 newtons. The question is, how far will the skater slide before he stops? One given answer for delta x, 120 meters. As you can see in the diagram, the velocity of the skater is going in this direction, while the force of kinetic friction is acting against the skater's motion. And in this case, we're going to apply the Newton's law along the x-axis, where the resultant force is the product of the mass and the component of acceleration along the x-axis. The forces acting, or the only force that acts along the x-axis, is the kinetic force of friction, and it has a negative sign because it's opposite to the motion. Then from here we are going to put the numbers we have in the problem. That is 36 for newtons for the force of kinetic friction divided by the mass 60. We're going to get minus 0.6 meter per second square. The minus sign shows that the skater is going to decelerate from a velocity of 12 meters per second until he stops at 0. To find the displacement delta x by using this value of acceleration together with the given initial and final velocity, and plug all these values into the kinematic equation v square final equal v naught square initial square plus 2a sub x delta x, and from here we are going to get delta x equals 120 meters.